Hello, I'm Alvise Pizzella from AI Hanover, and welcome to this pre-recorded talk about tilt-length coupling and Differential-Wavefront-Sensing Optical Bench Simulator, or TDOBS. So, this is a brief outline of the talk. I will briefly speak about TDOBS and describe how it's the schematics and the operation, and then I will speak about the current experimental progress and the future plans. So, this is TDOBS, so it's simplified version of LISAâ built in a ultra stable optical glass, so zero-dur. It consists of two optical benches, so on the bottom there's the LISAâ optical bench, which is the real simplified version of LISAâ, while on the top we have this telescope simulator which just provides the beams, so LISAâ-like beams for the LISAâ optical bench. In more detail here you can see the telescope simulator, and the main feature of this is to basically have this flat top beam generator, which allows us to simulate both the flat top beam or Gaussian beam, so the long arm interferometer and the testbed interferometer. In a simplified optical scheme you can see here how these two optical benches lie in the vacuum chamber. So what's there? We have three beams. The first one is a local spacecraft beam, so it's found now on the TX beam, and also we have a far receive beams for the RX beam, and as last frequency reference beams, which we call local oscillator, which have three different frequencies given the fact we use heterodyne interferometry. So the telescope simulator is able to simulate the beam tilt of the spacecraft by tilting the beams with two piezo actuators, and the tilts happen around this point called RX clip, which is where the LISAâ spacecraft would clip the beam received from a far spacecraft. So since this point is the most important point of the experiment, we have several optical copies of this, where we have placed two reference QPDs, one single element photodiode, a pinhole single element photodiode, and a phase cam. What do we do with these? So we use the reference QPDs to measure DPS and DWS, so for keeping sure that the beam is always centered in the RX clip with DPS, DWS for further angular measurements. And with the pinhole photodiode we have actually a phase reference which does not depend on tilt-length coupling, since we use a pinhole, and this is used in case to cancel any phase contribution which comes from before the RX clip, such that what we measure later in the science QPDs, which we'll introduce now, does not depend on the previous path length. So on the LISAâ optical bench, on the other side, we have imaging systems which suppress tilt-length coupling by imaging the point of rotation on the QPDs, and finally the science QPDs, which we use to measure DPS, DWS, and phase, which would be in LISAâ the ones measuring the gravitational signal. So here's a small picture of the full setup, including the modulation bench, where we have first a 1064 nanometer iodine stabilized laser, from which we then managed to get three different frequency beams via some AOM double passes systems, which allow us to generate beams with Doppler frequency shifts which would match the LISAâ heterodyne band between 5 and 25 megahertz as caused by the orbital motion of the spacecraft. So before I presented what we plan to have at the end, this is actually what's available now. So we are missing the imaging systems and the science QPDs, but this system is still ready to do some science. So we already have two reference QPDs, which basically have the same situation as the science QPDs, since it's the same photoreceiver, and except for the beam compression, they do have some system which can rotate the beam, keeping it centered on them, as in this case it's the actuators which would rotate the beam around the RX clip, which is an optical which this photo has an optical copy of. From now on you can actually neglect the TX beam, and our tests have been run using RX beam and local oscillator beam, which start from the same optical bench. So for what regard phase measurement, we have at the moment two phase meters available. So a 16 channel phase meter breadboard, which was used so far, which has not so good performance at high heterodyne frequencies, and a LISAâ phase emitter system pre-development, which is what we are moving forward to, which actually has a new digital phase locked loop architecture, which allows us to track the phase of a bit node independently actually on the initial of the heterodyne frequency. So then I come to the experiment operation. So how do we operate this experiment? So first of all, we need to start calibrating it, and for this we have added an auxiliary QPD, which is the pillar of all calibrations. So it's the only component of the experiment which can actually be calibrated. We do calibrate the DPS signal of this photodiode by laterally moving the photodiode with some translation stages, and this allows us, given some beam shift, to understand how much it has moved. We use this because then, while rotating the beam around the RX clip, so the beam stands still on these reference QPDs, there is a shift on the auxiliary QPD, and we use this shift to calculate how much the beam has rotated, and while making a DWS measurement, we can know how much we measured the DWS on the reference QPDs and the DPS on the auxiliary QPD, and we can therefore know what was the actual geometrical angle between, let's say, RX beam and local oscillator beam on the reference QPDs, and then we can perform the calibration here. So we get kind of a linear relation for small angles between DWS and DPS, or yeah, the angle formed by the beam on the reference QPD, and as evident here, this TDOBS method brings us to have a gain of around 5,000 when it comes to angular measurements. So it's a very precise method to measure angles. So that's why LISAâ is using it, because LISAâ requires an nrad angular precision in order to keep the alignment within the spacecraft while in operation. So as of now, we are investigating TDOBS noise because we want to reach this precision in the lab. So what we do is to actually measure DWS for long times on both reference QPDs, and then calculate the spectrum. So as you can see here, we have the spectrum of both reference QPDs, which actually are affected. So our DWS signal is affected by some common noise source among the two, and so by taking a differential measurement of the two, the situation quite improves. So at the moment, we think that this is due to some stray light, which we're going to soon investigate in the future. We repeated the measurement also at 5 MHz heterodyne frequency, where we achieve a very similar situation, and comparing the two differential measurements in one plot, yeah, they're extremely close. So yeah, this is our next big future investigation. So we also have some future plans regarding improvement of the experimental conditions. So we plan to temperature control actively the vacuum chamber in which the experiment lies, in order to suppress low frequency temperature variations. And we're also working on a new phase emitter architecture to track the phase of a quadrant QPD. So if you are interested in this, please take a look at this pre-recorded talk by Christophe and Pascal. And last, we are planning to test schemes of possible redundant detection, since the addition of a beam splitter after imaging system creates some astigmatism. This is not an already settled task. So thank you for your attention on behalf of the TDOBS team. So as we have shown so far, we do have a test which is able to test LISAâ's key technologies, and we are looking forward to improve and reach this DWS sensitivity which is necessary for LISAâ. Thank you for your attention.